네, 잠시 후 2시부터 제21회 국제방재협력 세미나
We will soon begin the International Disaster Prevention Cooperation Seminar, so please come into the venue and be ready. Take a seat. And please make sure that you wear your masks all time in the venue and also put your phone into vibration mode. Thank you for your cooperation.
네, 조금 뒤인 잠시 후 2시부터
We will soon begin the 21st International Disaster Prevention Cooperation Seminar. The seminar starts at 2 p.m. And due to the COVID-19 pandemic, we also kindly ask all of you to wear your facial mask when you are in the venue, except for the time that you are consuming some food. And also make sure that your phone is in the vibration mode or silent mode during the conference. Thank you.
행사 식순을 조금 안내해 드린다면 잠시 후 이제 행사가 시작
So from 2 p.m., we will open the seminar with the opening ceremony. The ceremony will take about 5 minutes, and after that, we will have a group photo session before we move to the keynote speech.
네, 본격적인 행사 시작에 앞서서 통역 리시버 채널
And we also provide interpretation service for today's seminar. Please find the receiver in front of you, and channel 1 is for Korean and channel 2 for English.
네, 안녕하십니까?
Good afternoon, ladies and gentlemen. Welcome to the 21st International Disaster Prevention Cooperation Seminar. First of all, thank you for making time to attend today's seminar and come all the way here to Daegu. And let me introduce myself first. My name is Shin Hye-rim, and I'll be the host of today's seminar. So the seminar marks the 21st anniversary this year. And as far as I know, it has been held online due to the pandemic. So it is first time in 2 years to host this offline event. And it is great to see all of you in face-to-face in this venue. So I'm so happy to see all of you today. So marking the 21st anniversary of the seminar, we are gathered here, and this is hosted by the National Disaster Management Institute. And you can also join us online as well using the YouTube channel. The live streaming is provided both in Korean and English, and if you have any comment or opinions, please leave it in the chat box. There are many things that are very special and important for our life, and data is, of course, one of them. Utilizing this precious data, we can better manage disasters and better prevent disasters as well. So the title of today's seminar is Digitalizing Disaster Management Using Big Data, and we have very special guests from home and abroad to deliver their special insight for all of us. We will first open the seminar with the opening remark and have a group photo, which will be followed by keynote speech. And later, we will also listen to a lot of speeches from various speakers as well. So we have a very important dialogue for disaster management today, and I hope and believe that this will strengthen the safety of our society in Korea. So let's open the 21st International Disaster Prevention Cooperation Seminar. And we will now open the stage for the opening stage. Please welcome Mr. Lee Jong-seol, the head of National Disaster Management Institute. Please welcome him with a big round of applause.
Greetings, everyone. I am Jong-seol Lee, Director General of the National Disaster Management Research Institute. Since the COVID-19 outbreak 2 years ago, we're finally holding the 21st International Disaster Prevention Cooperation Seminar offline with various experts in the field of disaster safety at home and abroad. This seminar has been held every year since 2001 to find solutions to emerging issues in the field of disaster safety and to acquire advanced disaster safety technologies and policies. And it's getting more meaningful every year. This year, as our seminar is held in conjunction with the K-Safety Expo under the theme of digitalizing disaster management using big data, we're looking very much forward to hearing various insights on utilizing ICT in the field of disaster safety. And we are proudly joined by Seung-jin Meng, President of the Korean Association for Crisis and Emergency Management, Bong-chul Seo, Professor at Iowa University, United States, Yuta Izmi, Professor at Muroran Institute of Technology, Japan, Sun Kwon-yoon, Researcher at Seoul Institute of Technology, Panayotis Kolios, Professor at Kypros University, and we're also joined by Young-ju Kwak, researcher at Ministry of Land, Infrastructure, Transport, and Tourism, Japan. All these experts have taken their valuable time out of their busy schedules, and we would like to express our deepest gratitude. Also, our thanks go to all our attendees online and offline. Recently, abnormal weather has occurred around the world, causing great damage such as heat waves, heavy rains, and wildfires all over the world. In order to protect ourselves from these disasters and promote safety, we must be equipped with the ability to collect and analyze disaster safety data rapidly. To this end, we need a digital disaster management system that can effectively collect, operate, manage, and share disaster safety data. Only then will we be able to develop a technology that reads natural phenomena and human patterns and predicts the future and can be widely used in various fields, such as the private and public sectors, to establish scientific policies throughout disaster management, thereby creating a safety net for our society. It can make a huge contribution to building our safety network in our society. Minister Sang-min Lee of the Interior and Safety has also recently mentioned that the ministry would establish an advanced disaster safety management system in relation to disaster response and announced that they would further strengthen crisis response capabilities by integrating and managing disaster safety related data and management resources on a digital basis. So for this purpose, I hope that today's seminar will not only contribute to the development of international disaster safety, but also provide an opportunity to explore the future path by sharing each country's digital disaster management policy cases. I ask for your attention and support. Once again, I'd like to thank everyone for your attendance and participation. Thank you very much. Thank you very much, Director General Lee, for your opening address. So it's been 2 years since we met offline. So, before we begin our lectures, let's just clear up our stage for a moment.
네.
So we took our group photo and we will now begin our keynote lecture, which will be offered by Mr. Seung-jin Mang, President of the Korean Association for Crisis and Emergency Management. Please welcome him with a big round of applause.
So this is an international seminar, so I'm going to introduce myself in English first, but my presentation will be in Korean.
First of all, I would like to welcome all the honorable guests who came from different countries to attend this international conference. I would like to give my best wishes for the success of this conference. And thank you to all our international guests for visiting Daegu City. Make sure that everyone have a good time during your stay in Korea. Best wishes and good luck for everyone. From now on, I present in Korean. It will be translated into English. 네, 오늘 제가
So my presentation today is about measures to improve flood response capacity. And I'm a keynote speaker, so I'm going to give you some general information on this topic, covering all different items for today's seminar. So this slide shows the content of my presentation today: introduction, and water resources and natural disasters in Korea, and some flood damage cases, and measures to improve flood response capacity, and conclusion. So first, introduction. In the 1960s, Korea started to focus on modernization and economic development, as you are all well aware. And we suffer a lot of floods and droughts every year repeatedly. And one thing in Korea is that the Korean government has promoted various policies to support self-sufficiency in the food sector in particular, supporting some rice cultivation industry as well. And we've also developed a lot of water resources in order to provide stable water resources and supply for the people. But due to climate change, we witnessed a lot of flood damages in recent years in particular, which I will tell you more about later. And because of this, we saw some backward flowing of sewage and flood storage facility inundation, particularly during heavy rainfall season. So I'm going to give you some flood cases in Korea, and I'm also going to identify the main reasons behind this serious damage. And then I'll also give you some measures to improve our flood management. And I will show you a lot of pictures as well later. But because we have some foreign guests, I am going to tell you about the basic information on the water resources and natural disasters in Korea. As I said earlier, we do see a lot of floods and drought cases in Korea every year. This spring, we had a serious drought, and in summer, a serious flood. And I'm living in Cheongju City, and Cheongju suffered both this year. An annual precipitation level in Korea is 1,283 millimeters. That is about 1.3 times larger than the world average. But the water resource usage per each person is just 12% of the world average. It is because of a high population density on a small land. And we have about 132 billion cubic meters of water resources every year, but we lose about 50% of them due to evaporation and so on. So total available amount of water resources is just 57% of 132 billion cubic meters. But not all the available water resources are used directly by the people, because some go to the sea and some are lost due to various reasons. So basically, in the end, we only use 28% of amount of water resources that we have every year. So the current situation is not very good in terms of water resources. And in terms of natural disasters, we do have a lot of events: typhoon, and heavy rainfalls, and heavy snow. And typhoon is one of the most, well, okay, so typhoon can affect Jeju Island and some cities and regions in the southern part of the peninsula. So Ulsan, Pohang, Gyeongju, and some cities that are located on the southern coastal line are often affected by typhoon, particularly in July and August. And at the bottom of this slide, you can see that every year we have an average of 3.1 typhoons in Korea. So we have 3 or 4 typhoons every year, basically. And I'm going to give you some more examples of flood damage cases in Korea later. And those cases include some cases that we can find in Ulsan, Pohang, and Gyeongju areas in particular. So from this slide, I'm going to show you some flood damage cases in Korea. So on this slide, you can see that this black line is the uh, this it's an area that is highly affected by water. And within the circle, you can see that a lot of people are living. Some areas here are highly populated. So when the city is flooded, we have to worry about inland flood, particularly protected lowland. So here, as you can see, that Typhoon Chaba wreaked a serious havoc on the southern part of Korea in 2016. The maximum precipitation level was over 131 millimeters per hour. So this amount of water is so big. If you go into the shower and use the full maximum pressure for an hour, you may have a water amount like 131 millimeters. So you can see that this flood affected a lot of areas in the region. You can see that some levees were lost and broken, and because of a high water level, it caused a lot of pressure on the levee, breaking them. And if some vehicles are parked around the river, it can be flooded as well. And rising water level also moved around the suspended matters particularly into the city, damaging a lot of facilities and people's houses as well. So some of these images are repetitive, but you can see again the bridges are broken and levees are broken and damaged due to the flood. And at the bottom, these two pictures are important because
경지 지역
flooding can heavily affect rice paddy fields. This is one of the most significant damages that we suffer in Korea when we are hit by serious flooding. And another picture of broken roads. You can see that container box is moving around the city here. It is falling from the streets into the river. And you can also see that the parapet on the bridge has broken as well here. And here you can see some images of broken skulls and flooded vehicles and sediment and suspended matters in the city, and some flooding of houses. People are taking their goods from the house for drying. So Chaba went to Ulsan first, later to Gyeongju. So these pictures are from Gyeongju. About 60 vehicles were inundated or broken due to the flood and typhoon. So this picture shows the Gyeongju region. You can see a lot of numbers in the map. Well, actually, these images are not exactly matched with these numbers as I planned first, but this is the region that's affected by the typhoon, and damages Gyeongju suffered were similar to those in Ulsan. Roads, levees, and rice fields, and also cities and houses. And here you can see the case in Pohang as well. Pohang is a city that has a lot of rice paddy fields as well. So these fields were damaged due to the typhoon, and it suffered a very high level of precipitation during the typhoon as well. So all the damages are similar. And next year, in 2017, we had a very serious flood event in Cheongju City. The areas that are marked with red in those pictures here, well, as you can see here, it comes with the time mark as well. So if you go to 8 a.m. or 9 a.m., the rainfall level is really high, right? And during this peak, we lost a lot of people. People died due to the flood.
간파냐 뭐
And so for humans casualties, you cannot really calculate the amount of damage, but for different facilities, you could see how much of a damage and loss this flood or typhoon brought. This is the protected lowland. There is a Mio River, and there is another river joining it. And there is an agricultural field divided into 3 different parts. And then the water discharge facility kind of malfunctioned, and there was a box between one of these 2 areas. And as you could see here, it's quite intimidating. And all these paddy fields were flooded. And then we used our system to analyze it. And the red colored areas are simulated damaged areas, while the yellow ones are actual flooded areas, and they overlap quite well, right? And you're seeing the urban flooded areas here. Top left is a river that goes through Cheongju City, and you see all the wastes sedimented together. And then you see this Lotte Mart, a huge supermarket, also being flooded. And then the river flowing next to that is called the Seongnam-cheong, and it rarely floods like that. Because of this flooding, the entire city suffered so much. And the last government administration, the First Lady, actually visited our city to comfort our residents. It was the same year, but in a different area in Korea. A little bit above or north of Cheongju, so this is Gwesan. I showed you the satellite image of the area, and now you're seeing how the center of precipitation is moving around. And right here in Gwesan, the center is, has stopped. So that's where the entire rain is just pouring. There exists a Gwesan Dam, which caused a lot of conflict between different ideas or opinions regarding it. I'd like to show you a short video clip. I don't know if it'll play. Okay, I think it is working. We'll watch the two simultaneously. But only one is playing. But the one that's playing, I didn't film it. But top left, you're seeing Kwesan Dam. This is the dam for electricity generation. And in the part of that dam was flooded. And then in the bottom, for some reason the video is not playing. You don't even see the bridge. The water just overflew the entire bridge. And then that discharge came to the upper stream of Kwesan Dam. Oh, this is what I was supposed to press. Here you go. Very threatening, intimidating, scary. So the one who filmed this scene was also in a very dangerous situation, right? Every time I press a button, I see a different video playing. So this is the Kwesan Dam from downstream to upper stream. So when there's no flood, you see beautiful scenery around this dam, right? And there is a real popular tourist attraction. But due to the flood, as you could see, a part of this dam was flooded. Now, moving on to 2020, when Yongdam Dam was flooded. So we started from 2015 to 2017, now to 2020, right? And if you see the map here, Yongdam is right in the center of the peninsula, or South Korea. And the total precipitation was 459.0 millimeters. So the soil was accumulated and the water discharge was malfunctioning. And on the right here, you don't see any levee, right? Of course, the water level will rise and it's going to flood. And when that happens, all these artificial vinyl farms, the farmers want compensation for that, for their loss. So then who should, provide them compensation? That's one of the social issues too. Also, the riverside land of Kumgang River on the bottom left was flooded like that, and on the bottom right, you see the protected lowland by levee was also flooded. So our system analyzes all these flood cases. And the protected lowlands go through this process for analysis. First, you input the water level and storage of the flood area, and also the river water level, and also the flood discharge, as well as the structure properties. And then you run or create many different scenarios, flood scenarios, and apply them to simulate different cases, and you'll be able to figure out which areas will be flooded. For this is the analysis for urban area floods. So this is the result of our simulation or analysis. So when Cheongju met flood in 2017, our rivers flooded, right? And when that happened, urban areas also flooded too. So our water gauge was not able to hold all that waterfall. So all these apartment complexes, especially the basement parking lots, were greatly damaged. It almost acted like, or played a role of a reservoir of the water rain. It was an unique case. And then you use the stormwater management method, or SWMM, to analyze these cases. Till now, I talked about many different cases of floods, and now I'll move on to measures to improve flood response capacity. So looking at the causes of these floods, first of all would be heavy rainfall, of course, and topographical characteristics of Korea. And we lack storage structures because to be able to build these structures, you need consent from the residents in that area, but they rarely give you consent. And then, due to rapid urbanization, the vulnerability of the flood management increased. And then many people lack in awareness of flood damage. They may come up with short-term prevention measures, but they don't really look long-term. But what we need is a standard, design standard and maintenance. So the design frequency for the water that goes from upper stream to downstream is 200 years. But that cannot be all handled by the existing facilities in Korea, because they could only handle like from 80 to 100 years. And we also need a better river and watershed maintenance. And we also need some installation and operation of internal drainage facilities as well. So for improvement, what should we do? What do we need? The local or countryside rivers needs to be worked on more. So maybe we need to increase the frequency of 50 to 80 years up to like 100 years. Also, we need to install more flood control water gates and establish emergency discharge facilities. And that's what we are doing actually, little by little, for the agricultural areas. But we need to do more. And this one, we need to build storage around a riverside. And it gives you some good example of Netherlands' Bisbosch artificial runoff storage. It's got about 24 weeks of residence time in the storage, which is very hard to achieve for Korea right now. Local governments are also keen, to pursuing this, but it's going to take some time and money. So and the National Fundamental Management Scheme also mentioned this, which is the redevelopment of the agricultural reservoirs. Also, establish flood disaster integrated monitoring system, particularly utilizing the digital big data. So up to now, I've mentioned all the things that we have been trying or working on. Very general stuff. But now I'd like to add one more idea to it, which is when there is actual flood, the central rivers are controlled by the central government, while for the rivers in the countryside, the local governments are supposed to control it, but they lack capacity to do that. So they only rather observe it. So we need to upgrade their capacity. So why not equip them with a flood simulator so they could better respond to floods, like the protected lowlands and other areas. They can be applied with the flood simulators. Conclusion. This is basically a sum up of what I've mentioned. To better respond to flood, there can be some, political supports, and please refer to the handouts. I was given 30 minutes, and I think I used all my time now. So I'll conclude my lecture here. Thank you very much for listening.
학회장님의
Thank you. It was Mr. Meng from KCEM. The nature is beautiful, and it is the most beautiful when it's safe. We cannot prevent all natural disasters, but we can do our best to minimize its impact. And I really appreciate all your effort to minimize the impact of natural disasters on our society. Thank you so much for your great presentation, Mr. Meng. And we will now invite next speaker. With this session, we will have a lot of speakers, 6 in total, who will give us insights regarding digitalizing disaster management using big data. So you can join us online as well. If you are joining us online through YouTube, you can also leave some questions on the chat box that can be answered by our speakers later. The first up, the speaker is Mr. Seo Bong-chul, professor of Iowa University. His presentation is all ready, so please welcome Mr. Seo with a big round of applause. Hello, I am Seo Bong-chul from Iowa University. First of all, congratulations to the opening of the 21st International Disaster Prevention Cooperation Center, and I really appreciate the host of today's event, NDMI, and the head, Mr. Lee Jong-sol. Today, I'm going to tell you about some natural disasters, particularly flood disaster, and I'm going to tell you how the U.S., particularly Iowa, is dealing with this natural disaster. So there are a lot of natural disasters, and we also have to understand that flood takes up a lot of share in terms of natural disaster. And I'm going to tell you about Iowa Flood Center and Iowa Flood Information System, IFIS. And I will also tell you about the QPF, quantitative precipitation estimation and stream flow prediction, which I think is the most important for prediction of flooding. And I'm also going to tell you the data assimilation methodology that we use, that is streamflow data assimilation. According to an insurance company, Munich, this is the results. This is the statistics of natural disaster. First, they broke down the natural disaster into 4 categories. And the top 2 were meteorological event and hydrological event. And climatological events are increasing these days. And as Mr. Meng said earlier, we do see a lot of flood events, and landslide and heavy snowfall are one of the water-related natural disasters as well. Well, this pointer is not really working well. So if you look at the case number 1 and 2, these are the cases that took place in Iowa. The first picture is actually the campus of the University of Iowa that are entirely submerged by the water. And the second photo, here you can see the downtown of Iowa is inundated as well. Some of you may not know where Iowa is located. It is in the center of the US. And the total area is about the Korean Peninsula, combining the north and the south. So in 2008, you see a massive flooding event that took place in Iowa. So Iowa campus and downtown were fully submerged. And in 2013, the campus and dormitory were submerged by water as well. However, this time we had some wall that is blocking the water, so we prevented some areas from submerge. And we also had some flash flood event in Des Moines, the capital of Iowa, in 2018. And the next year, you can see that the total area in downtown, except for the baseball court, was submerged as well. So due to these various natural disasters, Iowa government decided to set up Iowa Flood Center, IFC. The goal of IFC is to develop hydrologic models for physically based flood frequency estimation and real-time forecasting of floods, and second, to improve flood monitoring and prediction, and 3, to share resources and expertise. So for this, IFC developed IFIS, a tool for natural disaster management. So we get real-time data from various sources and put in the data into the system. And the results and calculated data is shared with many other agencies, governmental agencies, private agencies, and the public. The most important thing here is that all this data and output is based on collective data from various sources, and all this data is available for the public as well. So we use spatial data, weather data, and stream flow data, inundation data, and rainfall data in real time. And we also have a virtual navigation system as well. It may not be very effective in terms of actual application, but it gives some idea for the people, and it can be a great experience for them. And across the nation, we have various radars, and in Idaho, we have 7 radars that are collecting various data real time. And the collected data and the precipitation level data and information is shared with the public as well, and it is later fed into a calculation model to provide more accurate information on flooding. And across the nation and across the state of Iowa, we have water stage sensors. In particular, in Iowa, we have more than 300 water stage sensors, and these are doing a lot of jobs. I'm going to tell you what they do later during my presentation. So IFIS is the system that we provide. So the main page shows this radar information, and it also offers some flood alerts. And if users click some area on this map, you can get more detailed information about the region. And if you select your interested region, you can get stream flow information and water level information of the region as well. You can also get information on accumulated level of rainfall over the past 2 weeks. And the reason is that the water moves along the stream in Iowa for about 2 weeks from one space to the end. So there are various menus that you can play with. You can get a lot of information on various rivers, streams, and you can also go to the Google map and search for your place to get more information, particularly flooding and water related information on your neighborhood. And we also provide a mobile app that can be downloaded by anyone. So if you download this, you can use the app on your phone to check flood information of any region. And next, radar-based precipitation estimation. In America, there are 130 radars across the nation, and around 2013 and 14, all of them were upgraded from single polarimetric radar to dual polarimetric radar. So dual pol can provide more detailed and accurate information. And the information from dual pol radar is stored on Amazon Web Service or Google Cloud so that anyone and the public have access to them for understanding or further analysis. And this is QPE algorithm. If we use single pol radar or conventional radar, we only have 3 variables, but because we added dual pol radar now, we have 6 variables in total. We get atmospheric pressure and the location of melting layer and the liquid type precipitation below the melting layer. So to get all this information, we use dual pol radar so that we can get more accurate information on all this. And if you look at this data flow here, you can see that there are 2 models. First model is to identify melting layer, and the second model is to rain or snow classification, binary classification. So this radar information comes into the system every 4 or 5 minutes, and they produce 2 types of output. First output is instantaneous rain map, and the second output is cumulative rain map, a daily rain amount and 2-week rain amount. And when we assess the accuracy, we use the on-site report. As you can see, we use rainfall stages, data from rainfall stages. So these gray circles are data based on single pole radar, and these orange circles are based on data from dual pole radars. And this line is the bias that compare the radar data and rainfall station data. So as you can see, if all these circles are close to the line, it means that they're more accurate. And this means that you can see that orange circles are closer to the red line than the gray circles. That means that these dual pole radars provide more accurate and precise information. And this data is based on 4 different algorithms, but the radar, but all these models are based on the same data set from the same radars. And this is an official product made by the US. And the second one is the first one is MRMS, and second one is NWSDP, and the third one is IFCR, and the fourth IFCR. If you look at the first one, and if you look at the second one, you see some spikes here and there. This is because of the wind turbines that are installed across the region. These wind turbines cause some interference for these radars, and that is why we see these red dots. However, if you look at the 2 images at the bottom, the map is so clean. This is because we used dual pole radars for these 2 models at the bottom. So it is so much cleaner and accurate. And here the slide shows that our result is very close to the result of MRMS without doing some calibration afterward. So our data is really accurate and precise. And the next slide shows the hydrologic simulation, and it's categorized based on the basin size. The first is about correlation, second is MAE, third is RMSE, and fourth KGE. KGE is the index that estimates the accuracy of hydrologic model. And you can see that the performance level differs slightly every year, but all of them seem to be pretty good. But one thing that we have to note of is that if the basin area is bigger, the accuracy level goes higher as well. And next, streamflow data simulation. But this slide shows the basic concept of data simulation. For each time, we will get the discharge observation data, and then we will see the data applying time propagation. So if we get another data next time, we can apply time propagation again so that we can get the final result. So NWS developed NWM, National Water Model, that's now being applied for all the regions and states in Korea. in the states. And if you look at the structure of the national water model, the four things that are in the black box are the core models. The first one is energy vertical flux. It is LSM, land surface model. And second one is waterway routing model or channel routing model. And the model grid for LSM is 1 kilometers, and for channel routing is 0.25 kilometers. And for LSM, we use NOAA multi-parameter model. And for routing schemes, we have three schemes: diffusive wave, saturated, and Muskingum-Kunji models. And one thing that you have to take note of here is that this is just the streamflow data simulation is only for LSM, so there is no reservoir routing. So for Muskingum-Kunji equation, we need discharge data from three stations. So when we get the discharge gauge or discharge observation, we put the data into the system, but there can be some error margins that what we call notch. So we apply time propagation concept here to complete the data assimilation. But if you look at the very last part of the equation, you can see that the assimilation impact is just for the downstream of the river, not for the upstream. In Iowa, we have about 140 gauges across the state. So these red spots are the regions where we can apply the result of this data assimilation. And next methodology is persistence. This is a baseline method to understand previous data. It doesn't require a model. It is very simple. In order to estimate the downstream areas risk, you need to understand the upstream risk first, upstream data first. So we may apply a very complex hydrologic model to understand the results, but the results are not always accurate. So sometimes you can use this kind of simplified model as well. So here you can see that the green dots are no model data, and red dots are national water model data. And if you look at the right column graphs, KGE graph, you can see that when we use data assimilation, persistent methods produced so much better results, more accurate results. And the same results are written in different types of graph. It is again based on the scale of basin. These gray circles are based on persistence, and red dots are persistent model with data assimilation. You can see that red dots produced so much better results. And so far, we conducted data assimilation using data from USGS only. And if you look at the image on the right side, the small basin areas or catchment areas are not benefiting from this specialized tool because they don't have the downstream gauge spot. So we wanted to provide some benefits for these areas as well. And for that, we needed rating curve. But there are over 300 sites where we need some data from, but we cannot go to all those 300 sites. So we used pre-existing data that we collected from pre-existing gauges and systems and produced a synthetic rating curve. So there are some uncertainties on this rating curve, so we are estimating and evaluating the uncertainty of the curve now. So green is USGS spots, and blue are IO flow centers water gauges, and the red are the areas where we are planning to add more sensors in the future on the request of the community. So in closing, I can say that our system and model provide more high space and time resolution data, and all this data is thoroughly shared with the public on our platform IFIS. But we need to improve uncertainty of this data in the future, particularly some uncertainties of the precipitation level. And because this model has a lot of parameters, we do have a lot of uncertainties in them too. And we also do have uncertainties in terms of the interconnectedness of all these variables. If we can understand separate contribution of all these parameters and variables, we can reduce uncertainties of all these factors, but it takes a lot of job and we are working on them now. And this is the basic idea for our future work. Well, we are working on that now. So small areas and catchment areas around the city, we are using a lot of flooding prediction models. So some are based on radars and some are based on mathematical equation. And these results do have some gaps and error margins. So as you can see here, 1 hour and 2 hour prediction has a lot of errors. If you look at 5 hour, 6 hour data, a prediction that is based on radar data analysis, it doesn't have a lot of peaks. But 1 hour and 2 hour prediction shows a lot of peaks, meaning it has a lot of errors. So in order to improve this, improve the accuracy of short-term prediction, we might have to utilize AI technologies more. And currently, we provide our prediction model to understand the flooding areas during the rainfall. However, in the future, we need to provide more information in order to provide more dynamic reports. And lastly, we are working on a flood map We do have a lot of voice recognizing services nowadays, including Amazon Echo and Google Home. So we are trying to link our program with these services too. This will be the end of my presentation. Thank you. That was Professor Seo of University of Iowa. Thank you so much. So if you have any questions, please raise your hand. I see a hand. Thank you. Hello, I'm Moon Ji-won from NDMI. I have a question on your presentation. Well, here you mentioned that flood inundation map is one of your future works. But earlier, you mentioned that IFES already offer some sort of inundation map on your platform, on your dashboard. Well, so I think that the geographical characteristic of Iowa and Korea may different from one another, but I want to know whether you focus more on the geography or city inland inundation. In Iowa, we have 99 counties, and for each county, we created this flood inundation map. But as you know, Iowa is one of the biggest corn-producing states of the United States. But if you go into the city, you have to take care of a lot of houses and buildings and many other facilities too. So I think that this flood inundation map doesn't incorporate all those facilities yet, but we will improve that further, incorporating all those facility informations. Anyone else? Well, I guess the presentation was just perfect. We have no more questions from the floor. Thank you so much for your great presentation, Mr. Seo. Thank you.
Moving on to the next presentation, which will be given by Professor Yuta Izumi from Japan's Muroran Institute of Technology. He will be talking about the ground-based synthetic aperture radar for disaster prevention. Please welcome him with a big hand.
Okay, so thank you very much for giving me this opportunity today. I'm Yuta Izumi, Assistant Professor at Muroran Institute of Technology. And today, I would like to talk about how the radar technology can be used for the disaster monitoring. And actually, I mainly focus on the radar technology, so-called synthetic aperture radar, which is a type of the radar, but used for the Earth surface imaging. So I would like to demonstrate what is synthetic aperture radar at first, and then I will move on the basic of ground-based synthetic aperture radar. This is main topic today. And then finally, I will introduce some applications in Japan. So the synthetic aperture radar is active microwave remote sensing technique that transmit microwave and receive scattered microwave from the Earth surface. And this image, Earth surface image by the radar, can allow us to estimate several phenomena in the Earth. For example, earthquake monitoring, urban monitoring, or land deformation monitoring, and flood mapping. And SAR, synthetic aperture radar, is different from the optical sensor in the left figure, which is generally used for the remote sensing. And since optical sensor relies on the sunlight reflectance, if we have the cloud between the land surface and the sensor, we cannot obtain the information under the cloud. On the other hand, SAR, since the microwave that SAR utilizes can penetrate through the cloud, we can actually observe the information even under the cloud. And also, because it doesn't rely on the sunlight, we can observe the image even in the night. So these are the image comparison observed at the same time by optical sensor and SAR sensor. And as you can see, SAR sensor, in the SAR sensor, the cloud contamination, which is also the problematic, especially in the tropical country, but also Japan and Korea, is actually it shows the less effect of the cloud contamination in the SAR images, and we can clearly see the images from the space. And of course, it can achieve very high resolution of the image. And what SAR actually receive is the backscattering intensity. Assuming that the satellite transmits a microwave, and this transmitted microwave is scattered, and part of the microwave scattered in this direction, which is called the forward direction. On the other hand, part of this scattered in the direction to the sensor, which is called the backscattering. And SAR only receive this backscattering. Therefore, the backscattering intensity is highly dependent on the target. For example, if we have the man-made target like building, it gives a very strong double band scattering, so the intensity becomes very different. So this is an example in the left top part figure. We have the tree, truck, the truck, and a water surface, and the intensity is highly depends on the target because of the scattering mechanism different. So actually, the SAR image allows us to estimate and monitor several phenomena. And for example, we can obtain the digital elevation model and land deformation estimation and crop discrimination. And especially these can be achieved by so-called SAR interferometry technique and polarimetric SAR technique. And these are the top very important technique in our field. And today I will demonstrate SAR interferometry technique to demonstrate the GB SAR deformation monitoring. So let me first introduce what is SAR interferometry. So interferometry technique uses phase information. Actually, the resolution cell of the SAR image includes not only intensity information, but also the phase information. And this phase information is a function of the range distance between sensor to the target. So assuming we have two observations in different time, and then we have some subsidence between these observations, since the distance is changed, phase also changes. So if we take the phase difference between these observation 1 and 2, we can actually achieve to estimate the deformation amount by this equation. So this is a simple concept of the differential interferometric SAR. And if we apply this, this is an example of the results that I processed in Ojiya City in Niigata Prefecture, Japan. Here you can see some deformation over Ojiya City. And if we plot the time series of this deformation within 2 years, there is some seasonal deformation trend. And actually, this image result shows only the subsidence in the winter time. This is because the city uses extract the groundwater in the winter time to melt the snow over the road. So such kind of phenomena can be observed from the space. So in Japan, we have the so-called SIP program, stands for Cross-Ministerial Strategic Innovation Promotion Program. And this is a national project for social problem, and it promotes cross-ministerial, multidisciplinary efforts through the industry, academia, and government collaboration. And actually, we have several themes, and one of the themes is enhancement of national resilience against natural disasters. And in this project, they plan to use synthetic aperture radar because of the advantage of day and night observation and less cloud contamination. And they plan to launch several satellites in the orbit, which is called and then we can shorten the time from the trigger until observation for the disaster damage assessment and decision making by government and secure evacuation routes. And synthetic aperture radar is a sensor that can be mounted on any platform, moving platform. And these are the example of the SAR platform. For example, we have airborne SAR, shuttle-borne SAR, ground-based SAR that I present today, and drone SAR. So I will introduce the ground-based synthetic aperture radar now. So these types of the radar installed on the ground, which is different from the satellite SAR, have several advantages. For example, it can achieve real-time continuous monitoring, which where the satellite cannot achieve this task. And also stationary monitoring because it fixed to the same position and different observation angle and geometry from the satellite. So the GBSAR can observe that satellite cannot observe. So thanks to such kind of advantages, several applications have been investigated and performed so far. For example, landslide monitoring by GBSAR, volcano monitoring, glacier velocity monitoring, and bridge deformation or oscillation, vibration monitoring. So this is a case when the track pass through through the bridges and the bridge deformed, and GBSAR can detect this kind of the vibration and deformation by interferometric technique. So I would like to show the video how the GBSAR is operating. So this is, it cannot, yes, sorry, how can I, this one? Yeah, it cannot. But anyway, so GBSAR is moving along the rail, and then it transmits and receives the scattered microwave while moving. And after we collecting all the scattering signal, we can reconstruct the SAR images, which represent clearly the object shape. So let me introduce how GBSAR can achieve deformation monitoring in near real time. So to estimate the deformation, GBSAR should collect the signal. And then after correction, we can reconstruct the SAR images. And then if we repeat it, and then after we observe at least 2 SAR images, we can estimate the deformation between these observation images. And then if we repeat it, we can achieve near real-time deformation. This is the concept of how GBSAR is operating. And this is a general architecture of GBSAR, which consists of some signal generator and transmit and RX antenna and some microwave components. The important thing is that GBSAR uses frequency modulated continuous wave, where the frequency is linearly modulated with respect to the time. So after we receive it, it provides so-called range profile. So this is the simple experiment I did. We employ corner reflector 21 meters away from the sensor. And then this is an actual range profile, which exactly shows the 21 meter at the maximum point. So this is the concept of the radar. But GBSAR is imaging radar, not the ranging technology in the one dimension. So how to do it? To generate the images, GBSAR collect this range profile at the many points along the rail. And as you can notice, that the distance between sensor to the target is actually depends on the position. So after we correct it, the range profile draws a hyperbolic curve. So after we collect the data, we apply so-called synthetic aperture processing. Actually, we do some signal summation along the hyperbolic curve and at the middle point of the hyperbolic curve. Then we can obtain the two-dimensional position information after this processing. So if we apply this concept to more complicated scenario, we can obtain this radar images. So after we reconstruct the image, we can now start to process deformation. So as I already mentioned in the introduction, it utilizes the phase information, which is a function of the range distance between sensor to the target. So assume we have some displacement, and then if we take the phase difference, we can observe this displacement between this time. And if we apply this concept to all the resolution cells, we can generate the deformation map. So now I would like to introduce some applications, case study in Japan. So first application is a landslide monitoring by ground-based radar. So in Japan, in 2016, we have the so-called Kumamoto earthquake, which is very big earthquake. And the series of earthquakes induce the large landslide, which destroys the road, bridges, and actually killed one university student. And then the government started to do the restoration work along over the landslide affected area. And since many operators for the restoration work to reinforce the slope, the Tohoku University installed GBSAR just in front of the landslide affected slope, and then we started monitoring from the 2017 and up to 2020, which is a 3-year monitoring, and we provide the deformation information every 15 minutes. So in fact, it's very far away from our university, around 1,083 kilometers away. So in the observation site, we have the ground-based radar and local PC, local storages. So after the GBSAR collect the measured signal, the imaging algorithm implemented at the local PC produce the SAR images. After reconstruction, these SAR images was transferred to the PC at Tohoku University. Simultaneously, it was stored at the local storage. And then after the PC received the SAR images, it started to produce deformation map. And then this deformation map will be used for early warning system and daily report. Actually, we issue the daily report every day, every morning, 6 a.m. for the operator who working on the restoration work over the slope. And to notify, to give the information of the last 24 hours deformation. Thanks to the restoration work, we haven't observed the large displacement so far, but we observed very interesting phenomena, so I would like to introduce this. In fact, the excavator for the restoration work accumulates the soil for making a path for restoration, and then we repeatedly observe only this accumulated soil area, the deformation of the accumulated soil area in the night. Maybe this is because of the soil erosion by the wind. And we also we observe this kind of very small displacement by the ground-based radar. The second example is at the corner reflector. Actually, we deploy several corner reflectors over the monitoring site. And this is a deformation time series at the corner reflector. And as you can see, it shows some daily trend or oscillation. In fact, corner reflector is made of metal material. And as you know, the metal material shows some deformation due to the temperature variation, so-called thermal expansion. So GBSAR actually detects this thermal expansion phenomena from the 1 kilometer away from this very small corner reflector by interferometric technique. And in fact, during the observation, in 2019, we have very small secondary landslide occurred due to the rainfall. As you can see here, it is very small, but it actually occurred before and after the landslide. And then, I'm sorry, this is not related to interferometry, but we use polarimetric SAR technique to detect this landslide in nearly real time. So here, you can clearly see some abrupt decrease or transition of the parameter before and after the landslide occurred. So as you can see here, the GBSAR also can be used for the change detection in near real time, like this example. So this is a second example of the monitoring in Japan. The Unzen Fugendake, located in Nagasaki Prefecture, erupted in 1990. And a new lava flow, as you can see from the left bottom figure, was appeared in 1991. And the people and researchers are very concerned about the corruption of this new lava dome because of its weight, rainfall, or earthquakes. So the Japanese government initiated a ground-based monitoring campaign in front of this lava dome, as you can see, using this ground-based radar from 2011 up to now. And in fact, there is a 1 meter displacement observed from 1997 and 2011, and then actually it is moving. So this is a result of the deformation estimation by spaceborne from the satellite and ground-based SAR. Actually, the deformation vector is different for spaceborne and ground-based SAR. And in fact, ground-based SAR is more sensitive to this direction of the lava dome displacement than the spaceborne SAR. So this is also one of the advantages that GBSAR can estimate the deformation that satellite cannot estimate. But this kind of the combination using spaceborne and GBSAR is highly important for radar technique to apply to the disaster monitoring. For example, first we use the spaceborne SAR to detect the potential area or risk area in wider field. And then after that, after we detect by using the spaceborne SAR, we install GBSAR to obtain more detailed information for the local area that detected by the spaceborne SAR. And I hope this kind of the combination will be the standard technique for the disaster monitoring by radar technique. So this is the last slide. Thank you very much.
네, 무로란 대학교 유타 이즈미.
Thank you very much, Professor Yuta Izumi. If you have any questions for him, you're more than welcome to raise your hands.
분 있으시면 손을 들어주시고, 네, 마이크 넘겨드리도록 하겠습니다.
So we have one question.
I'm Hee Nyang from Contact. And yes, as a remote sensing person, what we do is we see the result. I mean that what we do is we get the result from the post-event, right?
Yes.
But in terms of using GBSAR,
Yes.
it sounds like maybe we can make a technique or make a scheme so that we can see the landslide susceptibility,
Yes.
something like that.
Yes.
So do you have those kind of plans to do it? Because the thing we've seen from your slide, the spaceborne SAR can be used to monitor the displacement in their line of sight from the space to the ground. So it means that, okay, we can see the thing from the space and then it can be used for the early warning. And then you guys can make a decision-making process
Yes.
that GBSAR is needed in that place and that we need to monitor those kind of things.
Yes.
So if you guys have some scheme or process to make a decision to install the GBSAR or something like that, could you please explain about that?
Thank you very much for your question. At first, actually, GBSAR have two objectives. First objective is to prevent or anticipate the landslide, because there is some studies that before the landslide occurs, there is some slow displacement. If this kind of phenomena happen, we can detect and we can actually warn some landslide will be happen soon. But the second objective, this is actually currently we are working to mitigate the secondary landslide or kind of investigate the stability of the land surface. So we install in the Kumamoto area for this purpose actually. So yeah, so this is actually practical case, I think, because usually the prediction of the landslide is very much difficult task, because usually we have the vegetation before the landslide, and vegetated area we cannot monitor. So I hope this can be this kind of the technique, as I mentioned, can be combined with the space-borne SAR and also can be applied to many landslides, because I heard that in Korea we have several landslides due to the rainfall, and after the landslide occurred, we can install GBSAR, because of course there are many persons who working on the restoration work. So to mitigate the second landslide and to protect them, it is very important for this kind of monitoring.
네, 고맙습니다. 충분한
Thank you very much. Is there any other questions? If not, I would like to thank Professor Izumi one more time for his great lecture. Please give him a big hand.
입니다. 지금 시간
So we've listened to two professors so far. Maybe we can take a break here. I'll meet all of you in 12 minutes. So let's resume the second part of today's seminar at 3:45. I'll see all of you very soon. Thank you.
네, 문 밖으로 나가면 왼쪽 편에 화장실이 준비가 되어 있습니다. 그리고 문 앞쪽에 옆쪽에는 간단한 다과가 준비되어 있으니까요. 쉬시는 동안 간단한 다과도 함께 즐겨주시면 되겠습니다. 네, 여러분 예정된 시간이 됐습니다. 회의가 된 관계로
So it's time to resume our seminar. So we will begin the second part of the seminar right now. So please come into the venue and take a seat.
네, 참석해주신 내빈 여러분께, 기빈 여러분들께 다시 한번
Once again, please, I kindly ask all the guests and participants come into the venue so that we can start the second part of the seminar. I know that not all of you are from the Daegu city, so we have to think about the trains going back home too. So please come into the venue so we can start the seminar now.
네, 2부 주제 발표를 시작.
Okay, so we'll begin the second part of today's seminar. Please understand that we've delayed a little, but we will resume the seminar right now. So the third speaker today is Mr. Yoon Sun-kwon of Seoul Institute of Technology. His presentation is about utilization of hydrometeorological big data for mitigation of urban flood disasters in a changing climate. Please give him a big hand. Okay, my name is Yoon Sun-kwon, and I'm with Seoul Institute of Technology. First of all, congratulations to the opening of the International Disaster Prevention Cooperation Seminar, and thank you for inviting me. Today, I'm going to tell you about utilization of hydrometeorological big data for urban flood management. So this is the content of my presentation today. First, let's talk about climate change and disasters management. And second, big data and smart water monitoring system, particularly the system established by Seoul City. And third, a flood early warning system in Seoul. So first, it's about climate change and disasters management. Well, you will all know about this already. We see an increasing frequency of extreme weather events due to global warming and climate change, causing severe droughts and floods. So intensity and frequency are increasing simultaneously. So far, the temperature increase across the world was 0.74 degrees Celsius, and according to IPCC fourth report, the Earth average temperature will increase further, so by 1.5 or 3.5 degrees Celsius by 2100. So hydrometeorological conditions can be a triggering factor, and it can cause a lot of serious disasters and hazards, including tropical cyclones, landslides, wildland fires, coastal storm surges, and whatnot. If you look at the picture on the left, you can see that the global temperature has been tracked from 1800. So in the beginning, the upward trend was pretty mild, but after 1960s, the graph goes up dramatically, so it causes a lot of extreme events. So based on normal distribution function, if you look at the right side graph, you can see that we are facing a new normal in terms of climate change. So we saw some increase in mean, as you can see in this graph, meaning that some tailing data and factors are increasing accordingly as well, causing a lot of extreme hot weather events and extreme weather events. So based on the results between 1990 and 2016, you can see that the climate change is causing a lot of damages. This is the image for the Beaufort Sea. And according to IPCC, this climate change is caused by human activities. So the Hudson River in New York will see a water level increase dramatically in coming decades. So a lot of land around the river will be submerged. The same goes for Korea as well. Incheon and some nearby areas, some areas close to Seoul metropolitan city will be submerged largely, because we expect the sea level will rise a lot. So it will affect the capital of South Korea dramatically. So climate change is affecting not just Korea, but the entire globe, of course. And this is a very important factor that we have to deal with in terms of disaster management. And if you see the graph here, the temperature increase in Korea was 1.4, while the global average is 0.9. So we saw 0.5 degrees Celsius more increase in the average temperature in Korea compared to the entire globe. So we are very susceptible to a lot of risks caused by the climate change. And this data is pretty old, but you can see that the frequency of disaster increased by 4.5 times, and the damage level increased by 10 times. So what is important in terms of disaster management? Of course, we have to improve our prediction first.
있는 그 예측 정보 활용 부분인데.
This is about how to utilize the data from NOAA. This is seamless prediction and its service. So we can think about very short-term monitoring. So radar and satellite images can be of great resources for short-term estimation and prediction. But we can think about long-term monitoring and estimation as well, and considering climate change. So we can use this data for various applications. So when we have this data set, well, this is the report from RI of the US Ready, Set, Go framework for early action across time scale. So this is something that we have to think about. So we might have seasonal data first, right? Then we can pre-process this seasonal data so that we can get ready. And we will also have some mid-range data, like data for 1 month or 2 weeks or 1 week, right? So with that data, we can go into the set mode. And then we will have short-range data sets. And with this data set, we can go to the stage go. So meaning that we can take actions in the early stage. And according to Peter Webster, a very famous meteorologist of the US, using this kind of different time scale data is really important. So seasonal outlook can be used for long-term planning, and 20 to 25-day forecast can be used for broad-scale planning as well. And the short-term data, like 1 to 10-day forecast, can be used for more detailed planning. And in the past, we had very complicated and complex process for the post-event management. However, I think that we have to focus more on the pre-processing now so that we can better prevent and mitigate the risks. So we always need to prepare for the next event utilizing all available data. And then we have to extend the length of warning and evacuation process as well. So we can utilize long-term data, particularly for flood risk management. This can be one of the risks that we can focus on right now. So when we think about integrated flood risk index, first we can talk about the flood hazard, a physical hazard, and we can also talk about the exposed values and their vulnerability. So for local governments all across the Korea, we can provide this seasonal outlook so that we can have more integrated information for our preparation work. And let's move on to the second chapter of my presentation. It is about big data and smart water technology. We have a CCTV-based monitoring system installed around the Junglancheon area of Seoul. We've worked with the NDMI for this project. So to provide alerts, we've utilized pre-installed CCTVs around the river areas. So this is the algorithm that we used. We used image processing for this algorithm, and we also tracked particles. So if particles moved dramatically in a short time, that means that the water velocity and discharge is large. So based on this particle movement, we could calculate the velocity and amount of discharge. And on the right side, you are seeing a video footage. This is the monitoring data from Gwanak Mountain. And you can see that we are measuring the velocity using this image. and Jungnangcheon and Uicheon were our target of the study. And we also combined Sangsucheon and Baeguncheon to better understand the entire water flow. So we worked with NDMI and we installed various CCTVs for our operation, and this is still a pilot project, but we are working with many other agencies as well. We have 3 CCTVs and 3 ultrasound wave gauges so that we can collect a lot of images and data in order to calculate the velocity of water. So here you can see full HD CCTVs are installed and ultrasonic wave monitoring systems are in place as well, and all the data are sent to our web-based system so that we can access the system anywhere, anytime. So this is the CCTV based collected image for the Uicheon Basin, and these black dots in the graph are are showing the velocity of the water. And on the right side, you can see that 3 images. These 3 images are from 3 CCTVs, and these images are used for our monitoring services. And as I told you, we have this web-based system which allows us to use the real-time data anywhere. So Han River is a really important river in Seoul City, and it is joined by 4 streams. One of them is Jungnangcheon, and we are expanding our project so that we can apply the system in Dorangcheon as well. And we are planning to apply this to Hongdaecheon and Tancheon in the future. And chapter 3, it is about flood early warning system in Seoul. I told you that seamless prediction methodology is really important for disaster management. So very short-term and short-term scale is the area that we have to focus on here. So it is about 1 or 2 hour data or 1 or 2 days data. So using this short-term data, we can improve our flood early warning system. And Seoul City suffered a lot of floods in the past, so we are doing our best to better respond to flooding. So one of the areas that we focused on is the river-based flood. Before the 90s, we suffered a lot of floods due to the river inundation. Well, we don't have that kind of issues anymore usually. Sometimes it happens around the Dorimcheon area, but not anymore in other areas. But after the 2000s, we saw a lot of problems caused by drainage system inundations. So that's the area that we have to further improve in the future. And as you know, in recent years, Gangnam Station and Dorimcheon region were flooded due to the heavy rainfall. Well, of course, it was due to extreme heavy rainfall that can happen once in 500 years, but still it affected a lot of people. In Gangnam region, some areas were submerged with a water height of 1.6 meters. So it caused so much damage, and this year, the total cost of the damage was estimated to be about 80 billion won. So we have to better utilize a very short-term data. So radar data and satellite data can be of help. And for short-term data, short-term prediction, we can utilize GRIMS and WRF model. So using all this data and methodologies, we can have a better short-term prediction result. And we also have COMS, Chilean satellite, which is now monitoring the typhoon information from above. And we can get real-time data from this satellite, of course. So for example, this data is not delayed over more than 10 minutes. So it's like a real-time data. So for 1 to 3 days, we use WAF model. And so all these collected data can help improve the accuracy of our prediction results. So this is one of the story areas that I'm focusing on right now. It is Torimcheon Basin. It is very vulnerable to flooding in Seoul. So we believe that radar-based data can be of great help in order to better predict the risks from flood. And as you can see, this solar system is very complicated around this region. So if we do the simulation using all this total network, it can take so much time. So we use a simplified network so that we can simulate this way faster. So if the rainfall is over 300 meters, you will see the results. You will see some areas being inundated, and the result can be seen in the bottom picture. So this is the structure of inland river combined flood early warning system in Seoul. And here you can go and check it yourself by the URL included in the slide. So it is a web-based warning system. You can go and check it on your own. And we have SBB, Smart Big Board, for disaster prevention in Seoul. This SBB is also collecting a lot of data for wildfire and transportation issues, including traffic jam. So all this data are collected through IoT-based sensors and smart sensors and monitors all across the city. So when we collect all this data, we can provide early warning for the public. So this is how we are utilizing the big data. So we have sensing data and image data. So all this data, along with AI technology, is working so well in terms of improving the accuracy of our prediction. So we will do more research on this matter to improve the accuracy. Thank you for listening. Thank you very much. It was researcher Yoon Sun Kwon of Seoul Institute of Technology. If any of you have questions, please raise your hand. Okay, there, I see one hand. Hello, I'm Jung Ji-e from NDMI. Thank you for your presentation. Due to the extreme weather, we see a lot of torrential rain events. In order to reduce the risks and damages from them, you are using CCTV images and many other data sets. But in terms of management of this, I believe that scaling up this project can be challenging. So do you have plans for expanding this project to the level? Yes, I showed you the example of CCTV-based prediction model. And this is about flooding prevention, particularly around the Seoul region and around the rivers that have a lot of that are very vulnerable to flooding. But when we had the serious flooding this year, the affected areas were not limited to the rivers. It affected the roads, bridges, and even households, particularly basement flats. So these days, the flooding is not due to the river, but to the water supply system or drainage system. So SIT is focusing on this change as well. So if we better utilize the CCTV, we can better gauge the water level of the river, but we can also have more information on the city and streets as well. So if we can get data from CCTVs all across the city, we can, of course, have more accurate prediction and preparations. So inland flooding became a really serious issue. So CCTV-based information and IoT-based sensors can offer a very precious information. Thank you. That's very good question and answer. Thank you for your answer, Mr. Yoon, and thank you for your great presentation. If you have more questions, please leave them in the chat box on our YouTube channel. It will eventually answered by our speakers later.
교수님께서
Next, we'll invite Professor Park Seung-hee from Sungkyunkwan University to hear about intelligent disaster response decision support system using big data. Please welcome him with a big hand. Good to see you all, everyone. My name is Park Seung-hee from Sungkyunkwan University in the Architecture Engineering Department. And I'm very delighted and honored to be here in a very meaningful event. And thank you for inviting me here. It is an honor. And within my given time, I'll try my best to deliver what I've prepared for you. So the main theme for the seminar is digitalizing disaster management using big data. It's a very future-oriented theme. And we've heard some great presentations today. And we need to proactively respond to these disasters, and we need to secure the golden time for active response. And for all this, we need the real-time on-site data. And when there is a decision maker's opinion intervened, you cannot really have objective or third person's view on the case, right? Everybody says we need to be more scientifically respond to the pandemic. But as you could see, the things are not going that way. In a disaster management field, there is no one perfect, correct answer. Nobody can come up with one. But when we do utilize the on-site real-time data, we can come up with better schemes for active, proactive response. So we first need to digitalize existing data. So in this regard, I am, carrying out my studies too. We talk about big data, but actually data is very limited. So it is the role of the decision maker in the control tower to choose the most optimal option among these limited range of data in the quickest possible time. That is why the decision-making support is critical. We do utilize big data, but final decision is made by human, right? But to make the most reasonable possible decision, we need this big data support. So moving on, it has been mentioned many times today already, which is that climate change induced unexpected disasters are occurring more and more, and its intensity is even growing more. That's why it is very difficult to optimally respond to these type of disasters. You're seeing right here as one of examples the wildfire. Before, we used our experience, right, accumulated experience to respond to wildfires. Many agencies are now more shifted towards utilizing data for early detection of the fire, real time or preliminary detection. On your left is the report of the wildfire status, and then on the right-handed side, it shows you like increased disaster intensity with climate change. But all these decision making had been very kind of manual, and all these monitoring and CCTV and satellite imaging and remote monitoring and the real-time data collection and everything you've mentioned here today. We are saving all these data, but the DB-based learning, which is big data-based AI, is what we're lacking a little bit. Such process needs to be carried out on a scientific manner. A wildfire is just one example, but most of the disasters are in the same situation in terms of response. So S-brain, referring to smart brain, or you could also call it a safety brain. Dr. Yoon also mentioned the big data collection. I mean, we are collecting all these data intelligent process, through intelligent process. Human brain carries out so many different processes simultaneously, right? It processes so much data, and it makes prediction, and it also carries out optimization to finally make a decision. But like I said, no answer can be perfect. But you could at least come up with ways, a decision that could proactively respond to these disasters. So that's what we're trying to design in the big data AI process, data processing. That's why we need to, that's what we call a platform. It's an AI brain. So it collects data and processes it and makes a decision and provides different paths, safest path, the quickest path, and everything. So this AI platform studies a lot. It learns, for example, like our GPS navigation app, right? So we need to make this platform learn as much as possible to come up with the most optimal decision, which we could refer to when we make, decisions. So disaster response related decision making has to more rely on this big data system. We all talk about machine learning, deep learning, and reinforcement learning. All these technologies are applied to this AI brain or platform. That's why but it's not good enough, and because its learning is very limited, that's why we also apply different learning effects inducing solutions like transfer learning and everything. And that's the specific area that I am also carrying out my studies. As you could see here in the center, there is database and how to effectively manage it and how to pre-train it and fine-tune it and add new data set into it to come up with more reasonable decision making is what we need. For example, like unmanned aircraft, past weather data, and disaster history, and drones, and sensors, and smartphones. All these resources are abundant. And I am sure this National Disaster Management Research Institute has also come up with a lot of studies related to this issue. As we all know, think about this Naver, Kakao, they all have their own platform. I mean, Korea is like really a data powerhouse, which we could all utilize to come up with a high quality disaster response platform. I have limited time, so I'll make it quick. It's very important to have intelligent disaster safety management. We talk about resilience. When we use this AI-based support system, we could definitely shorten, our work interruption time to come back to normal. So, for example, you get into an accident and you're hospitalized, and you're in an urgent situation. It takes doctors quick, most optimal decision in the moment to respond to your emergent situation, right? That's what it needs for disaster management as well. And when you collect data, it can be classified into different types: structured, semi-structured, and unstructured, and everything. And we also need to pre-process it. And then you systemize all these data. However, the optimal operation of these data on the platform is an issue that needs more studies. Like I said, more essential elements and information for the most reasonable decision making, we need to really extract the essential data. All the public agencies and government ministries have all that, the data source. We just need to compile them together and process them together, which suits the intelligent platform. You see the AI engine on your right here on the screen. You'll see this like reinforcement learning and transfer learning, data mining, you have an image information. It's all that takes to be able to come up with the relevant warning regarding, a particular disaster. And the decision maker, human decision maker, can communicate with the AI support system. So you can make more scientific and reasonable decisions. And this is the simplified version of what I've just mentioned all this time. Like I said, though, this is not a one correct, definite, absolute answer. No one can come up with one, like I said earlier. But we still need to do our best to come up with the most optimal solution. On the right is the decision maker, and AI system is a support system. Not the AI system itself does not make a decision, but it supports the human decision maker. And I've carried out this process for wildfires. The AI solution detects wildfire and it calculates the area of the wildfire based on the past wildfire history and cases. Although it does not, it's not 100% correct or precise, but it showed a high percentage of precision. And it is getting better and better even today. And you could also utilize chatbot technology to detect how, visualize the progression of the wildfire. On your left is for preparedness, and on your right it's for response. Due to limited time, I'm just going to skip. You could refer to this images later on in your handbook. But this is the platform that we're working on right now. This table shows the disasters occur in spatial information, right? They can be calculated and detected in the spatial information. That's why you have this table to collect different types of data in real time for intuitive decision and analysis. Decision making can be calculated or concluded. Also, real-time on-site data-based visualization of the situation can be mapped out like this. It also visualizes the hospital accessibility. And on this kind of map, you can also include the wildfire risk map too. Also, you have to include the information on shelters, of which the number is very limited in each area. Give me 2 more minutes. The serious disaster related punishment act is carried out right now, right? Which means the safety accident, which really happens on construction sites. So big scale disaster management may have a difficulty utilizing big data, but on these construction sites, which are more shallow, big data can fully be utilized with high precision. This is not an image taken, from general camera, typical camera, but this is a 3G advanced tool filmed image, and it can also be used for monitoring and prediction from this cyber and physical spaces. Like workers can communicate regarding abnormalities, and you could also check workers location and movement and control worker access. So you see the object detection. Throughout this process, we can support them with the reliant data relating this construction site. In conclusion, digital twin platform is what I mentioned earlier. It has to be equipped with a trainable platform. Although it may be imperfect, the AI is getting smarter and smarter, so we need to apply AI to disaster respond management system. So I will conclude my lecture here. If you have any questions, you're more than welcome to raise your hand. Thank you. Thank you very much. That was Professor Park Seung-hee from Seongyun-gwan University. Do you have any questions? Yes. Thank you for your lecture. I am Choi Sun-hwa from NDMI. The Intelligent Decision-Making Support System based on big data was a very interesting topic. I'm also keenly interested in it. What you suggested today, data is the most essential part of it, right? But in reality, disasters occur in various types. It has more than 50 different definitions, right? And a response, its entire cycle, it's just broad. So we need to collect even more data to build confidence for this system. So I think confidence and trustworthiness is very important. But yes, we do have data related to disaster management system quite open, but some parts are quite closed, and we actually lack data regarding some areas. So maybe it's kind of too early to fully apply big data and AI. So my question is, how can we better collect disaster and response related data into a big data to be able to really utilize these data to come up with this intelligent disaster management support system that you mentioned? So this quality and credential, reliable data collection, do you have any concerns or ways to collect those data? Thank you for your question. I've mentioned it briefly. Yes, we lack data in this very field. It is still a question mark regarding how we could collect such quality data. But many industries are, working to equip AI platform and everything, but they all have the same concerns. Where do we get all these data? And where do we acquire that reliable data? And there is also a legal limits for us to collect these data. I mean, it's kind of a global concerns. Sorry, I cannot give you very clear practical answers, but we could utilize transfer learning and deep learning and everything to better collect, to improve the situation. I mentioned the wildfire as my example. There is a background. It can stay same, but the smokes, or the colors of the wildfires, you could utilize them to create or produce or generate diverse pieces of data. That's what's called the data augmentation technology. It is meaningful because the reliable data are limited, but on the field, especially for disasters, random data could occur unlimitedly, right? So it can be imprecise for now, but for unexpected disaster-related data, you could come up with them, unlimitedly, and you could have your AI platform learn those data. That's what we are trying to do. So please understand where we are and what we're trying on. So data augmentation is where we are focusing on. So I think that is a way for us to, overcome those limits. Thank you very much. Thank you for a great lecture, Professor Park. Please give him another big hand.
네, 여러분 다음 두 분의 발표는 코로나19 상황.
And next, well, please understand the next two speakers pre-recorded videos in advance due to the pandemic. They are restricted from traveling, so please see the video and please understand that you can't raise your questions this time. The next speaker is Professor Panayos Kleos from University of Cyprus. The presentation title is AI in Emergency Management.
So, hi everyone. My name is Panayiotis Koios, and I'm a research assistant professor at the Kios Research and Innovation Center of Excellence of the University of Cyprus. My presentation relates to AI technology used in emergency management, and I will delve into the tools and algorithms that we have been working on within Kios to help out and develop technologies that will be used by first responders in the field. So let me start this presentation by a high-level introduction to Kios. Kios is within the University of Cyprus. We are 180 researchers right now, mostly research engineers and software engineers in the fields of computer engineering and electrical engineering, computer science, mathematics, physics, physicists, and civil engineers, and so on. And we are based in Nicosia in Cyprus, and we are focused on developing information and communication technologies for monitoring, control, management, and security of critical infrastructure systems. So the critical infrastructure systems that we are looking at are a power grid, water distribution networks, intelligent transportation networks, healthcare as of late. I'll show you a few of the things that we did for healthcare in a while, telecommunication networks, and of course, as an umbrella, technology, emergency management and response. So with respect to the healthcare, of course, as you all know, the COVID pandemic has been influencing a lot our life in the last 3 years. So GIOS has been collaborating closely with the Ministry of Health in Cyprus, and we developed all the tools, all the ICT software for helping out in fighting the effects of COVID. So we have been developing the contact tracing apps, the collection and the digitization of all the tests that have been going on, the certificates for the negative or recovered patients, the whole hospitalization and recovery of patients in other systems. So up to date, we have been developing and maintaining and supporting the Ministry of Health with different software, web-based technologies, software tools mainly for fighting the pandemic. And I think we, as the Republic of Cyprus, I think they have done a good job, and through these systems they were able to better manage this enormous uncertainty related to COVID. And within Europe, we are one of the most successful, let's say, countries in managing the pandemic and recovering from the effects of the pandemic in a fast and rapid manner. With respect to R&D of the center, we have been looking at and developing technology through different European funded projects, including several from DG ECHO. DG ECHO is the Humanitarian Aid and Civil Protection Agency of the European Union. So the latest projects that we are finalizing now are AIDES and Artion, related, focus specifically on developing artificial intelligence tools for first responders and how to disseminate the knowledge we gain through these projects to the first responder community. Other projects related to law enforcement agencies from the DG Home. DG Home is the internal security and border agency of the European Union, and several projects that we have been collaborating closely with first responders and law enforcement agencies in this area is related to border surveillance, and Seretab is one of them. And in a few months, a larger project called Reaction is starting to tap into the technology that we have been using and bringing it to the field. So we are rolling out the technology that GIOS has developed to actually being implemented in the field for getting a faster situational awareness regarding border surveillance. And of course, we do a lot of R&D, so research and development within the Horizon 2020 and Horizon Europe framework for science and technology development. We also have a strong partnership with industry in Cyprus and in Europe. We're focusing on many projects related to developing first responder technology. And then also we are part of the Union Civil Protection Training Mechanism for sharing the knowledge that we have gained and the tools that we have with first responders in order to be able to have a greater impact to the community. So some of the technology that we have been using to develop our software tools include drones. Of course, a lot of first responders are eager to introduce drones to their operations. So we have a large testbed infrastructure at GIOS related to drones and unmanned aerial vehicles. So we have fixed wing drones, as you see there, multi-rotor drones, where we try to develop software that can control autonomously these agents, these drones, and get the sensor readings, analyze the sensor readings in real time and show the results to in a user-friendly way to the first responders in order for them to understand what is happening on the ground. In addition to this kind of technology, we are also developing mobile command and control centers for analyzing the data in real time in the field. Also cloud computing servers for processing offline this data and build the intelligence for the algorithms to be able to be executed in real time, and also customize the off-the-shelf hardware. As you can see on the right here, we add different sensors, different actuators, customize it for the different application needs that arise in different projects. In addition to developing the technology, we participate together with the first responders in field exercises to test the technology. So search and rescue exercises, simulations of earthquakes, floods, and of course fires, where we try to investigate the impact of our technology in the field. And also we have been asked to participate in real situations as well, in order to help out when there is these large-scale events that are hard to control by the current means and teams of the Republic. In addition to UAVs and data analytics, we also have we are continuously rolling out proprietary IoT infrastructure, mostly for preventive activities, so monitoring the environment and the critical infrastructures, especially in Cyprus, and understanding how they operate in order to be able to then respond faster in case of disasters. So over the years, we have came up with this list of very important things that first responders would like to know during their response phase to large disasters. So we are categorizing all the information in 3 classes. One of them, as you can see in all cases, it's situational awareness. So for example, in fires, we want to know the flame height, the color of the fire, the temperature, the spread rate. So these are very important information for situational awareness during uncontrolled fires. And then using information for the weather, the vegetation type, and so on, we can do better forecasting using models of fire propagation, for example. And then the third category is location information about teams, about the buildings, about accessibility to the road network, and so on. And you see all these 3 categories repeating for the different disasters like floods, earthquakes, and the pandemic. And we are trying to develop algorithms and tools that get information about all these 3 categories and all this information related to the large-scale disasters in a real-time fashion. So analyzing the data, receiving the data, analyzing the data, and then showing the results in real time, so that first responders are able to know exactly the situation on the ground, be able to do decision support, be able to do decision making faster, and also automate, where possible, automate the whole process of decision making by robots, for example. So this is the activities that we have been doing for developing the technology for the different phases of the disaster, including early warning systems, systems that automate the search and rescue of victims, modeling and predicting the cascading effects of disasters, doing mapping and reconnaissance in situational awareness in real time, and so on. I'll show you some of the examples now of this technology that we developed using either onboard hardware, hardware at the ground control stations, or hardware at the cloud premises. And all these things have been possible because of the higher computing powers of all this hardware, the ability to collect more data, input data from sensors, and new AI algorithms that we have been developing over the years. So one of the things that we can do with images in real time. This is from a small drone with an embedded device that processes the image coming from a camera on the drone. And then you can see how detection and tracking of objects can happen in real time. So you can measure densities, for example, you can measure the dynamics of the environment and so on, that are very important for understanding the ability to do, for example, evacuation of the area. Another example of search and tracking is for objects to be followed and not just be detected and know the location, but also follow these objects. So in this case, again, a very small drone with an embedded device, we developed an Android app where the images are now processed on the Android app, and then the user just selects which object to track and follow, and then the drone knows how to do so in real time using the embedded devices that process this information, see the location of the object, and then instruct the drone to go to this new location in order to be able to have the object always in the center of the field of view. Let me remove the sound from here. Another technology that we have been working on over the last several years is for the preventive phase of the disaster, is to inspect autonomously critical infrastructures using UAVs. So in this case, you can see here we have attached to the UAV the normal RGB thermal cameras, but also a multispectral camera that helps out identify the vegetation type and the humidity and the risk of this vegetation getting burned during the summer season of the year. So the drone goes through these medium voltage and high voltage power lines in this case. So this is infrastructure inspection of the power grid. So the drone goes to some predefined coordinates. It looks for the poles because these coordinates are not accurate enough. As you can guess, this is very old infrastructure, so there is no precise location of the coordinates of the infrastructure. So the drone analyzes the data received from the RGB camera, detects the pole, then goes from one pole to the next, and then analyzes again the data to see if there is any vegetation coming to proximity to the power lines, and then indicates the location of these obstacles so that people can go and clean the area and avoid the risk of fires. In addition, as it detects the power lines, it also detects the insulators and looks for any insulator faults on the power lines, on the poles. So it does this in a fully autonomous fashion, especially in the forestry area, which is much more challenging than the images shown here. And it gives a risk index of the area that needs to be looked at, and in order to minimize the risk of fires burning during the summer season. In addition to the prevention and response activities, we also do recovery activities. So in this case, we have built an algorithm for stitching images and develop a 2D and 3D model of the area after disaster. So this is after the large-scale fire that burned last year in Cyprus. We went with the drones using different sensors, LiDARs, multispectral cameras, and so on. And we investigated the possibility of developing this high-resolution, large stitched map of all the area that has been burned out, and assessing how many trees have been burned and so on. Another thing that we have been looking at is how to introduce new tools, AI tools for smartphones and web services. So as you can see here, we developed a small smartphone app, a lightweight smartphone app that runs in different versions of Android for people to report their location, take pictures, videos. These pictures and videos are analyzed in real time, and then incident commanders can see what the first responders on the ground are seeing, and also exchange information with them, again, images and videos and areas of interest and so on. So this is a way for people to coordinate better their activities during large-scale search and rescue operations. Another example is the fusion of data. So imagine now that we have, again, on a UAV, different cameras and different sensors. The idea is to investigate how data fusion can be used to better get information about all these needs of the first responders that I presented before. And one of the things that we have done, we have fused weather information with LiDAR information and multispectral camera information in order to better forecast the propagation of fires in real time. So we fused all this information in an algorithm that is able now to better predict fire propagation over time. And this is the platform we developed for the first responders in order to see the results of this data fusion in a nice GIS system. So here, for example, we just show, to understand what we are doing, we show the different bands of the multispectral camera, but then we analyze this information from the different bands of the multispectral camera that is overlaid on a map, and then predict this fire propagation using the weather data we collect, and also, as I said before, LiDAR information about the topology and the elevation of the ground where the fire is progressing. And lastly, I want to focus on the flooding disasters. We have looked at, with first responders, a lot of different challenges of these flooding scenarios. Of course, the first thing is how to I understand where the teams, where the means, the victims are. So we have been looking at machine learning algorithms for small object detection. You can see here how hard it is as you go higher and higher and the objects become smaller to detect these small objects, and we have been developing algorithms to do so. But we have also developed algorithms for all the different phases of flooding where pathogens could also be present. So within a project called PathoCert of the Horizon 2020 DRS call, we have been looking at how we introduce technologies for better monitoring, control, and management of incidents related to water contamination. And one of the technology that we have been developing and testing here at the GIOS is for the water sampling, autonomous water sampling with UAVs. So in this case, we developed a tube that is attached to a UAV. As you can see here, the UAV has the electronics to be able to control this tube. It goes to the area where the possibly contaminated water is. Then using sensors, it knows how deep to dip this water tube in order to get a water sample. Then the water sample is taken from a proper depth of the water. Then the drone takes off again, returns to the home location, and the first responders can get a quick test of the water before they go into the water for evacuating people. So if they have to wear proper suits and so on. So we have been looking at how to do this, and now we are in the process of testing it with first responder in field exercises. So lastly, I wanna summarize what I have shown here. We developed the tools for first responders related to the different application needs that I demonstrated before. Then we test this in field exercises, and we help out in deploying this technology and use it in practice. We try to disseminate information and give all these tools out freely for first responders to use across the world. So if you are interested in our website, we have links where you can go and download especially all the software and the data sets we have been collecting. And finally, I want to emphasize that we are part of the Union Civil Protection Mechanism for training first responders on how to introduce these new technologies to their operations. I would like to thank you very much, and please, if you have any questions, send me an email, and I will be glad to guide you and help out. Thanks a lot.
네, 고맙습니다.
Thank you very much. This is a pre-recorded video by Professor Panayos Kolios. Although he's not here, please give him a big hand. When we first developed CCTV, we thought that that was a great leap in the civilization, but now it is being applied for various areas, particularly for disaster prevention. It is so interesting and astonishing.
곽영
Lastly, we'll hear from researcher Kwak Young-ju from Ministry of Land, Infrastructure, Transport and Tourism from Japan. He'll be talking about the long-term perspective of digital infrastructure management under climate change, and Mr. Kwak is also working at UNESCO. So we'll watch his video lecture. Greetings, everyone. I am in Japan. My name is Kwak Young-ju, and thank you for inviting me to this seminar. As much as I wanted to be there physically, but due to the prolonging pandemic, please understand that I am participating online. So today I'll be talking about the study result that I got 15 years ago at UNESCO. And this is a part of my personal study activity. As you could see, I'll be talking about the long-term perspective of digital infrastructure management under climate change. So, where I work right now, the Ministry of Land, Infrastructure, Transport and Tourism, we focus on all the disasters that frequently occur every year in different shapes and types, like landslides, earthquakes, volcanoes. So it is our prior assignment to proactively prevent these disasters and how we could respond and cope with those crises. Also, we also focus on equipping with strong infrastructure and maintain them. UN is pursuing the SDG goals, and Japan as well has come up with an SDG action platform, and in our ministry has also come up with projects building a resilient infrastructure and related policies and advanced technologies, for example, IT technologies or beam construction, automation, resolutions, and solutions. We are coming up with these solutions and also supporting them with different policies. So, on the global scale, what's the trend or the status of the climate change and its effect? This is my simulation result, and the input data that I used is from the Japan Weather Forecast Agency. And I used the major rainfall data, and I expressed it in the 20 kilometers grid global scale. I reduced it or converted it into the 500-meter resolution. I downscaled it, and it shows the discharge from the upper stream to downstream of a river, predicting the water depth in the flooded area. As you could see, the red pixel, red color shows the changes in 100 years. So you could see the red part, it was reduced by twofold, and in Eastern Europe and China, Eastern China, or in North Korea, their risks has doubled, and in India, especially in Himalaya mountains, the flooded plains, or Pakistan area or Cambodia flooded plains are, being noticed more. On the global scale, when you make predictions, you could notice the, bigger floodplains. And in the upper streams, you can predict heavy rainfalls. So in the upper streams, it doesn't show in this slide, but it's going to have higher risk of landslides. And how precise is it? We never know. But based on the actual real-time situation, you can create or apply it to your model to enhance the precision level. For example, you could use a satellite image to film the real-time actual field flood situation and compare them with one another. And then you repeat the process again to apply that to your model. For example, like in Cambodia, Bangladesh, or Pakistan, there were floods 25 years ago or 50 years ago. You use those models. A few weeks ago in Pakistan, there was a flood from which 1/3 of the land was submerged. And with my model, we already predicted it 15 years ago. In terms of Japan, there was a huge flood in 2015, and the Geospatial Information Authority of Japan, or GIS, they used the aircraft to observe the flooded areas. And they also utilized the topographical data to calculate the flood depth, and they provided the information. As you can see here, from the upper stream, the water comes down and it overflows the levee, and the levee is damaged, so affecting the downstream areas and just flooding the downstream area cities. In this type of situations, you really need to collect field data utilizing the satellite data images, and you could film it with drone to provide the data real time to the disaster safety headquarters for them to come up with the best response measures. Back in those times, our ministry had pump cars and other heavy equipment, and we provided the data to them so that they could come up with or see the accessibility of these heavy equipment to those flooded areas. So it's really important to collect data right before the flood happens. So the digital technologies that we used back in those times, first was use the GB radar to observe the rain clouds. And we never know in which area the flood will occur. So we needed to broad range monitoring. So the Japan Aerospace Exploration Agency ran their program, or the satellite radar system called ARIS, to estimate the raise of the river water level, and then we also need to match the timing of when the situation actually turns dangerous and also the timing that satellite can observe or capture. It's really hard to put these three things all together simultaneously. This is a radar image, so it's really different from ordinary color image. That's why you need a different technology to read. So differential detection technology to predict or to show in which area the levee was broken down or in which area the buildings were, swept away. You see those areas in pink. And in more complex areas, some other technology, for example, the coherence complexity, utilizing the phase difference to read the situation better, and precise data can be sent to the disaster headquarters. And we also offered or provided the data to the local residents for them to respond to the situation for follow-up management. So it's really important to predict, but the on-site response is also very important through digitalized data utilization. Predicting climate change is a difficult process, but knowing such crisis and not knowing such crisis there is a huge difference. So on the government level as well, or local government as well. So they all need to reflect such matters when they design a new city or constructing new infrastructure. That's what's important. Thank you very much for listening. Thank you. That was the last lecture. I'd like to thank researcher Kwak once again for taking his time to, record this video lecture. Thank you for, staying with us till the very end. The recent disasters and floods and everything are drawing attention of many people to this area. The rapid climate change will bring more disasters, and we need to prevent and manage such situations by utilizing our given data. Digitalizing disaster management using big data was our big theme of the 21st International Disaster Prevention Cooperation Seminar. This very occasion must have been a very important event in the global disaster management history. We were delighted to be joined by many experts and professionals from different fields to hear their insights. It was a very meaningful time. And we'd also like to thank everyone for staying with us till the very end of the seminar once again. Thanks to your support. This seminar was a huge success. It is our hope that what we share today will give a good influence on improving disaster management measures. We'd like to thank once again to the host of this seminar. Thank you everyone for your participation. This concludes the 21st International Disaster Prevention Cooperation Seminar. Thank you very much, everyone. Goodbye.